Welcome back to the channel. Today we'll talk about transformer protection using a differential relay. So assume that we have a big network. This is just on a DIgSILENT page. Assume we have a different transformer ratings. Okay, so how do we protect the transformers using differential protection relay? Well, normally we have to measure the current entering into the transformer and leaving the transformer. For example, if we have a fault in here, so we need to measure the city in here and then the city in here. So since the fault is outside the box of the transformer, then the relay should remain stable. But if the fault is within the transformer, we expect the relay to trip. So in here we don't have a differential relay in this one, but what we can do is I can walk you through step-by-step guidance how do we model. Let's have a look. Let's just open a new page. Okay, so the first thing what we need to do is just put a simple terminals and then just connect the transformer. Okay, and then we can just rotate this one. Let's bring that one. Let's just disconnect this one. Clockwise. Just connect now. And then connect here. Okay. So the question is, if we do city in here and the city in here, it does not allow us to calculate a short circuit in the transformer. Okay. So in transformer it's different than the transmission line. Transmission line we can create a fault directly to the device, but in here it doesn't allow. It is gray out in here. Okay, so one of the technique we're gonna use is to put either a node or a dummy cable, like a transmission line, for example, a small cable in here. So either we can use just like a node. A node is a separation between the transformer and the bus bar. So for instance, if we just connect here, okay, so that we can create, then we can just either we can use circuit breaker in here, or we can just use an empty cable, just a short cable basically. Okay, it doesn't matter. So at least then it will allow us to calculate a fault in here. As you can see now, we can create a fault in here. And on we have to fix, but at least it's not gray out. The calculation of the short circuit is not gray out now. Okay, so now let's build this one. So this is the bus bar. So assume now we're gonna do a step down transformer. So let's do this one 132 kV. Let's call it bus bar 1. Then I'm gonna select this one bus bar 1 in here, 132 kV. You can create your own if you want from here by a new table and 132 and the bus bar 1. Yeah, it's the same. Okay, and then I will call this one 33. So this is step down. I'll call this one bus bar 2. And then I'm gonna create, I can create in here an 33, but I have also defined already bus bar as 33 kV. Then assign to this one, and then I will call this one bus bar 2. Okay, and I have terminal 1. I'll just call it terminal 1. So this is 33. I'll call this one terminal 2, which is still 33, this one as well. So this transformer, the dummy cable is 1 kilometer. Okay, I can just call it line 1, doesn't matter. But in here I can, okay, 0 0. I'll just call it line 0, this one. Okay guys, and then I just call it line 0. So what it means is there's nothing impedance in it. It's just a short cable basically. We don't have a normal. We can have normally like, okay, practically we should have very small cable. Okay. So it's better to put like this. 0 3. I'll just call this one 0 5, for example. It doesn't matter. Or I just call this one, this is this 0 6 in here. Okay. So as you can see here now, a very short cable. Okay, just like almost 0.1 ohm impedance, maybe not 1 kilometer, even maybe 20 meter usually. What does 0 2? Okay, see, it's very, you can call this one, I can increase this one, no problem. 0 8, maybe this is now okay, that's fine, I can leave as it is. Maybe 1.2, maybe 7, doesn't matter, it doesn't matter. Okay, just for a sample now. So now we have almost 0.01 ohm. Okay, it's very short cable, usually to connect the transformer into the bus bar or into the tower basically. So, and then again in here I can just call it line 00, and then I will call this one, assign this one, just delete that one. It was just existing lines basically. So now I'll just call this one 00. It's the same cable, but in this case it will be 33 kV. Just change this one, and then the load is will come to that point, but 75, 1.75, because it's an LV side. Yeah, okay, just 0.02 again, very short cable. So the question is, we need to configure now the transformer, and either we can put the parameter in here, or I can still have, okay, let me just delete this one once, and then let's create a new one. So let's have 90 MVA transformer, 132 into 33. From that 12.5, typically transformer rating of 90 MVA or this kind of voltage rating. So XR ratio is around 20. Of course, the higher the transformer, maybe XR ratio is about 14, 15, or sometimes up to 30. It depends. So this is just 90% of this one, so around 11.25, and then we can just use this one. Same. What it means is we can calculate this mathematically as well to see the copper loss basically. Around 561 copper loss. Okay, so now in here, this is most essential. We can use YND11, or depend on the vector group or phase shift. Okay, so we can now run the load flow. It's nothing. Why? Because we don't have generator, we don't have load. So assume now we have a load in that side. Okay, so let's say our load is 80 megawatt to 20 MVR. So we need a generator to satisfy the load demand. Okay, I'm gonna just use a grid. Just rotate that one into that side. Just straight one, this one. So I'm gonna use load flow now into MVA, 100 MVA. Let's say for example, we just use 0.95 plug-in. Now run the load flow. Just adapt. Okay, as you can see now, our bus bar voltage is here. Just adapt 130 kV, 1 per unit. Yeah, and you can see here now this is megawatt, 80.5 and 30 MVR, 376 kiloamp. or loading current is now on the HV side 376 amp, and on the LV side loading current is around 1.5 kiloamp or 1500 amp. Of course it is the ratio of the voltage basically. Why? Because if we divide 132 to 33, so 132 divided 33 voltage, so around 4 times. So now if we multiply this 376 times 4, 376 times 4, which is around 1500. So as we can see, we have 1500 amp or 1.5 kiloamp. Okay, so now we need to do the protection relay setting. We know that the loading current is this much on the, so basically what we can choose is now we can use a CT. First of all, install CT transformer CT1 on the HV side. Let's call it CT1. I can call this one CT1, but now how do we choose the primary current of the CT? Well, we have 376 kilo amp in the primary, so that this we need to choose higher than that. So that let's say we choose 400, but typically let's say 600 amp in the primary. Okay, and then on the secondary side or in the LV, we can also put a CT2 current transformer 2, because sinus CT2, or we can just choose from here CT2. Since the secondary current is 1500, we can choose higher CT. I think I can choose maybe 2000. Doesn't matter. So I need to make this one 2000 because 1500. At least I need to choose higher than that. Okay. So I'll have my secondary CT 2000. Okay. Okay. So now we can run the load flow again. So the question is, how do we set the relay? So again, we have to put the relay on that side. Add new device relay. I can add relay. Can choose F87 line differential relay. Choose magnitude. Okay. So now the first is we need to edit this one, copy the CT into the relay. We also need to copy this CT into the relay. Let's just put in that relay, edit into that relay, CT in here, paste. So now we have the relay have a CT information, primary and secondary CT. Okay, I mean on the HV side and the LV side. So now we need to configure the setting of the relay on the differential relay. You have to click in here. So this release threshold is the relay pickup current. So we know that the relay pickup current in here it is, okay, let's do this way first. Okay, this is now a relay. Okay, so what it means is because our current is 376, so then our pickup relay is we can use slightly higher than this one. Okay, so we can just put 0.3 pickup current, because the 376 we need to divide by the CT ratio, and then we can just put in here something like that, and then I can here put this one 2, 10, and 30% the slope. If you want to know how we calculate this one, you can watch the previous YouTube channel. I've discussed that calculation. and restraint, the second slope we can use up to 60% or 70, usually up to 150. Okay, according to the IEC protection recommended setting is up to 150. I can just use this one as through fault 8 or instantaneous trip relay. Of course, it's a bit bigger size. Let's just make it a bit smaller. Okay, so now this is our relay, and what we need to do is now we need to plot or show on the diagram. Okay, here you go now. So this is now our relay characteristics. So this is the minimum pickup relay, and then this is the first slope at 30%, and then in here it is at 70%. We can choose this one into 150, for example, if we wanted. Then it become a bit towards the left side, or we can just lower this one up to 60%. It's basically how when there is external through fault current, we just increase the slope basically to avoid maloperation of the relay. Okay, and then this is at low fault basically. So now assume this is this, and I will create a fault. Let's create a fault in here. When we have a fault in here, the relay is expected to trip 25 milliseconds, as you can see. Of course, I create a fault in here as well. The relay will also trip. Look, yeah, in here. The question is, how much fault current is this? How do we know? Well, we have already discussed about this, but I can just put in here in this one 25 kiloamp. Just run this one. So the easiest way is just run the load flow. So this is the nominal current before the fault, and create a fault at this bus bar. So now we have 25 kiloamp. Okay, as you can see. What it means is if I change this one into per unit, just change this one into per unit in here. Just delete that one, we don't need that one. So this is this. So we can divide this 25 kiloamp divide by the nominal current, so to see by how much is bigger. So then if I create a fault on the line, so on the dummy line as well, so in here. We don't need this one, already we have that information. Okay, just delete that one. Honestly, not that one. That's not correct. Not this. Yeah. This faulty impedance. We can choose whatever we wanted. For think a faulty impedance. Okay, this is faulty impedance. Okay, leave this one, then I'll just use this one for now. What it means is this is the ratio of the printed ratio of the fault current 25 kiloamp divided by the 376 amp basically. So now we have this. We can calculate fault in here as well. Okay, then we can still check the relay if it trips. Yeah, it trips, and of course there's a lot of things to check it, but and then if I click in here, if I create a fault in this bus bar, because this bus bar is outside of the city, we are expecting the relay not to trip for this fault. Let's have a look. Yeah, 9999, which means the relay is not providing any information. It doesn't trip. It remains resilient, or it doesn't trip. Okay. So this is how we basically do the differential protection relay setting configurations. Okay. So of course we need to consider a lot of scenarios to ensure that the relay is correctly tripping. For example, we need to check. We need to consider CT ratio error, CT saturation, and loading at different load flow as well. Sorry, low fault levels. So, for example, we can maybe lower this fault level. Maybe what about if it is close to? So, for example, if it's 1 kiloamp, will that relay trip? So, for example, when we can lower the fault level closer to nominal current, because nominal current is 376 amp. So for example, if this is at 0.376, will the relay trip? That is also the biggest challenge for the relay. For now, it looks like, let's create a fault in here. Yeah, it can still trip. So that is the age. What it means is the differential relay is very effective tripping what is coming and what's coming out currents. Okay, so basically this is just very basic, not detailed transformer differential relay protection. Thank you for listening. Stay tuned for the next issue, guys. Thank you.